Doing on the current assignment, all done?
No, stop.
Okay. I know Damien had worked how many hours?
Many hours.
Maybe 2 hours.
Yeah.
I saw an email from Damien yesterday saying he had worked 70 hours on the assignment. And but he did a good job, and almost the last part. So anyway, let me do this, because what I'll do is I'll give you a solution to the assignment, partial solution, not complete solution, and explain, because otherwise it will take us too long if we want to get to the next level, and it won't leave as much time. So let me go over the key concepts, how we can implement. I'll show you. It's not too bad. Okay, see, for example, let's take a look at a batch normalization first, right? Okay, because that's one of the hardest parts. I think the other part wasn't too bad, where the second part of the assignment was, I think, atom implementation.
Yeah, that was.
Right? Okay. Anyway, for batch normalization, remember we had, and by the way, there's a few different variations of the batch normalization. Some of you who went on the internet, perhaps got confused because, their implementation was not exactly the same as we were doing. So in our case, we decided what we'll do is, here's the sum unit. Then from this sum unit, we'll create, what did we call it, SI hat or something, right? Then further gamma and beta, we called it SB. Then this will go through the activation function and produce, right? So in order for us to do SI hat, if you recall, this was S minus mu B over, S minus mean over mu square B plus some epsilon, which could be like 10 to the negative 6 or something, right? So then the SB was basically gamma times SI hat plus beta, okay? So anyway, first part was to go through the math, and this is our regular delta, and this is what we call delta Bn. Because if we can compute, regular delta is easy, right? Once we know the gradient up to this point, all we have to do is multiply that by the derivative of this activation function, and we'll get the gradient, right? So the tricky part was going from here to here. And once we are able to do that, then again, going further will be, we know the expression for sum, and we can do partial S over whatever that input is and keep going further. So it becomes the same as we have done before. Yes?
My question was, do we do this for every layer or just the last layer?
You can do it for one layer, or you can do it for all layers. Batch normalization can be applied to any layer. Okay, and intuitively, as we discussed, you should always question why are we doing this, so that you have an intuitive meaning behind it, right? So, just like it says, batch basically means it's not operating on a single input, it's operating on a batch of inputs. So if we take a look over here, if we did not have the batch part over here, then if we, for example, let's pretend this is two-dimensional data, even though in real life it will be very high-dimensional data, but to understand the two-dimensional data, let's say we have 50 items in the batch, they may be, some data points over here. So what batch normalization is doing is by subtracting to the mean of all of this data, essentially what it's doing is it's moving it towards the center. So all of this will now become something like this. Okay. Then further, this is basically doing some kind of scaling and then some kind of a translation. So the net effect is this will basically become a little closer. So like I said, we can apply it in every layer if we wanted to. In the assignment, I asked you to do it for one layer so that, you don't get too confused, but the answer I'll give you applies it to all layers, okay?
When we calculate SI hat, we calculate at the end of the mini batch.
Yeah, exactly. I mean, the mu b would be computed after the batch size, right?
So that's the complication,
Yeah.
and that's where a lot of you guys got confused, and let me show you. And Damien was in my office, so we went over this. Okay, so now as you guys said, what about this mu b? Isn't this the mean of the entire batch? Okay, yes, it is the mean of the entire batch. So if you take a look at our current implementation, in our current implementation, even in the matrix form, we were feeding in one input at a time. So does that mean you have to go through it twice? Meaning first, let's say this is 784 by 1. Okay, and let's say our batch size is 10. Okay, so this mean over here is basically, mean will also be 784 by 1. If it is the, sorry, let me not make it 784 by 1. 10. Let's make it over here. Let's pretend we have 100 neurons over here. Sorry, the batch size is 10. So this will be the mean of, so each will be 100 by 1 over here. So we feed in 784 by 1, right? Then for the batch, let me see what I'm trying to say is, if we have 100 neurons, we feed in one value. Yeah, so there will be corresponding, yeah, so let me clarify it a little bit better. Okay, so let's pretend we have 100 neurons over here, correct? So this is the top neuron, this is the 100 neuron. So everyone will have corresponding to one 784 by 1 input. As you can see, there will be 100 values over here. So in matrix form, S is basically 100 by 1, corresponding to one of the inputs, right?
Yes.
Okay, so if we have a batch size of 10, we are feeding in 10 inputs, you'll see there will be 10 of these. Each will be 100 by 1. You guys agree? Okay, so what do we mean by the mu b over here? That basically means add this plus this plus this, divide by 10, add this plus divide by 10. So mu b itself will be 100 by 1 vector.
Yes.
Okay, so the question is, how do we compute it? In our current implementation, we were feeding in one data item at a time. So that means first we'll have to feed all 10, compute the mu b, and of course the variance accordingly. Then refeed those 10 again, one at a time again. Because now we will know the mu b, and now we can pick each individual S and we can compute SI hat. But if we did it that way, even though it can be done, that's not very efficient, right? Feeding the same 10 things twice. So alternatively, what we can do is, let's redesign our implementation. Meaning, rather than feeding one 784 by 1 input at a time, we feed in 10 times 784. So we feed in whole batch as a matrix, okay? So it is a small change that we will need to do. So first, forget about the batch mean. Make the entire code batch-based. So in one matrix computation, it's computing all the matrices in terms of batches. So if S is not, so if we made it batch-based, then automatically within one input, this will become basically 10 by 100. Okay, then our NumPy has a simply mean method over here. So if we did np.mean and fed it as an example S and fed it x is equal to 0, basically we'll go start averaging on each row, and it will give you 100 by 1 mu b over here in one line of code. Okay, same thing np.var. S x is equal to 0 will give us the variance, meaning the mu square b over here. Okay, so then rest of the code becomes easy. So let me switch to the computer, show you the actual code, and I will give you most of it, except where you will be implementing the equations. One second. Okay, so anyway, also I had asked you to derive this. So anyway, I'll give you the solution, like I said, as long as you guys go through it, learn, that's what we care, regardless you were able to get the equations or not. So I'll put this on the website. So this was our picture, right? Based on this, as I had given you in the lecture, we go through, compute the delta first. So this delta over here. Then from this delta, we compute delta Bn, right? Okay, so anyway, these are our 4 equations which we'll use to compute all the derivatives over here. So the hard part was, like I was saying, up to here, partial loss over partial gamma, partial loss over partial beta was easy, right? Because there will be partial L over AI, partial AI over SB. This is just, could be a sigmoid or a ReLU or whatever, so this is standard. Okay. Then partial SB over partial gamma, if you take a look over here, will be simply SI hat, right? Or partial SI over partial beta. will be what? Partial SB over
One.
just one, which is same as this, which is same as
Right.
delta, right? So as you see over here, okay, partial L over partial gamma, delta SI hat, partial delta, so straightforward, right? The tricky part was going forward, which is delta Bn. By definition, remember delta means what? Delta means partial loss up to this point, meaning partial L over partial SI is what we call the delta, right? Okay, which is, as you can see easily from the picture, L over AI, A over SB, SB over SI hat over SI. Okay, so up to here it's trivial. From here to here it was tricky. Okay, because the equation, if you take a look at the equation for SI hat is SI minus mu B over sigma square B plus epsilon. So you can see it has to find mu B, but mu B itself depends on SI. Okay, sigma square B depends on SI. So it's not like, you know, we just simply do 1 over sigma square B plus, because these are further functions of SI, function of SI. That's what makes it complicated, right?
Yeah.
So as you will see, I mean, hopefully we'll go into another scenario where it becomes complicated. If you, you know, keep a discipline, draw the picture. Once you have the picture, then draw all the paths, then it becomes really straightforward to compute no matter how complicated the problem is. So basically, as we discussed in the lecture, now let's go to SI hat to SI. As you can see, there's an SI involved over here. So this is the SI, right? There's a mu B involved. So pretend this is doing the sum of all the SIs. There's a sigma square B involved. Pretend this unit is doing all that variance calculations. So there are 3 paths going into it. As a result, as we discussed in the previous lecture, this will be SI hat over SI plus SI hat over partial mu B times partial mu B over SI, so this path. And lastly, the third path, correct? Okay, now we go one at a time. I called it 1, 2, 3, and we start evaluating those. So hopefully some of you, I know, were able to do it correctly. Since the answer was given, so I'm not sure if you actually came up with the right answer or simply said, okay, this will be the final answer. Okay, the trick again that you will run into is, let's go to, for example, the second part over here, right? Okay, in the second part over here, if we did mu B over SI, let's take a look at the equation for mu B over SI. Okay, so what will be mu B over SI?
1 over n.
Okay, and the reason is, think of it this way. Pick one example. Suppose we were doing partial mu B over, so suppose we were doing partial mu B over partial S2, right? If I expanded this out, wouldn't this be S1 plus S2 plus S3 plus whatever divided by n? Right? Now it's easy to see if I did partial by S2, these all disappear. Oh, and with respect to S2, it's just 1. So the answer is 1 over n, right? Okay, let me ask you another question. Can you tell me what will be partial mu square B over partial mu B?
Summation is I minus mu B squared.
Okay,
Lec squared.
Is
So
that
summation
so
is
will it be
minus-
just, for example,
2 over n.
2 over n? Yeah.
okay. So if we did this, right? So think of this is 1 over n, S1 minus
Mu B1.
mu B square plus S2 minus mu B square plus so on. Okay, so the mu b is appearing in every term over here, correct? So as you guys saw, this will be 2 over n into S1 minus mu b plus S2 minus mu b plus whatever S9 minus or S10 minus mu b, whatever, right? However many we have. Everybody agrees?
Yes,
And then further, the derivative with respect to mu b,
-1.
so there will be a negative over here.
Yes.
Okay, now what's the answer for this one? Okay, if I add up all of these, won't this will be S1 plus S2 plus S9, right? If I added up all the mu b's, what will that be?
And you,
N mu b. You guys agree?
Mhm.
And now if I divide by n, what happens? This becomes n, this n disappears. But what is this then?
me,
That's mu b. So mu b minus mu b, what happens? It zeroes out. So that's why this term appears, goes to 0, okay? Let me ask you another related question. So see, whenever summations are involved, this is where a lot of people get confused, okay? Just expand it out just to a few terms, and then you'll be very easily able to see that what will be the answer. So for example, by the same token, let me ask you this. If I did, this is sigma square b, right? If I did sigma square b related to SI, will it also be 0?
Maybe. We need to yeah.
should be only one term.
1 by n, so.
Okay, it will only be one term. Why? Because again, pick this to be, let's say, S2. So you can see this has nothing to do with S2, so this zeroes out. This will become 2 S2 minus mu b, and the derivative with respect to S2, which is 1. So it will be just one term, okay? So anyway, that was the trick. So in fact, many people have written blogs on batch normalization. Quite a few I found, were partially not simplifying it to what it can be done. So anyway, so once again over here, I tried to show you the same thing. So now I'll put this on the website. So once you go through it, now everything will make sense, and what you will end up with will be the final answer that we had expected in the assignment. So this will be the answer. Okay. So now if you program it, like I said, the key is, because we need the mean of the batch, we need the variance of the batch. So we have to turn our code into the batch matrix form, okay, into the tensor form, okay. So now let me sidetrack and show you the code.
Professor?
Yes.
I have a question. Partial SI hat over partial SI. The mu and the sigma has SI in their formula.
Okay, let me put this back. Okay, which one are you talking about? Partial SI hat over?
Over partial SI.
So the first term.
Yeah.
Yeah, so that simply will be minus mu b over sigma square b plus epsilon.
It should be -1, but there is SI inside mu b and there is SI inside sigma squared b, right?
Oh, yes, you're correct. There is an SI inside mu b. But see, okay, the
Yeah.
short answer to that is we already took care of it when we split it into 3 paths.
Mhm.
Okay,
Okay.
so in the other 2 paths, because the mu b sigma square b, we had created a separate path to it, so that's why we don't have to take into account over here. Okay, so anyway, back to the code.
So the for loop would be changing, right, in the code?
Yeah, so let me start with the code and so let me show you what changes you will make. It's literally is a 5-10 minute change. It's not a major change you need to make. So first let me open the code that you guys already are working on. So if I go okay, so anyway, let me contrast this to the changes you will make. So let's start with, for example, our let me go to the network class. A little bit easier. Size is declared. Okay, so one of the changes you will make is anytime you see a 1 over there, okay, like for example, our train Y was 1000, comma 10, comma 1, right? Just make it 1000, comma 10. So eliminate the 1, okay? Very similarly over here, 10,000, comma 10, comma 1 will simply become 10,000, comma 10, right? So anywhere, for example, for computing the deltas, computing the S's, previously we had a 1 involved. So let me, for example, go to the layer class. Okay, like take a look over here, size of the delta. Okay, do you see it's a number of neurons, comma 1? So if it is 10 neurons, it will be 10 by 1. If it is 100, it will be 100 by 1, right? So just make it, take out the 1. So just 10. Just this one. Okay, so why are we doing that? Like I was saying, the motivation is like this. Let's say we feed our input x, right? From now on, rather than we feeding it to be 784 by 1, it will be fed as 10 by 784, right? Okay, our weight matrix, for example, is 100 by 784, correct? So as we multiply these two, so in one shot at the matrix level, we want the output in terms of the batch. So as you can see, S will be, if I did W times X transpose plus B. Okay, W is 100 by 784. X transpose will be 784 by 10. You guys agree? So then, or should we do X times W transpose? X times, let me do X times W transpose. I think that would be better. X times W transpose plus B. So X is 10 by 784. This will be 784 times 100. Yeah, that will be better. And this is 100. Okay, so as we multiply these two, as you can see, this will automatically produce a 10 by 100 answer. Okay, so same way we can proceed onwards. So basically, like I said, the major change was slightly in the matrices so that we match the dimensions properly. Okay, so this was the original code. Let me show you the modified code, which I'll provide to you. Okay, so basically, this is a separate project I created so that we don't disturb our old code. So you can do that, just import all the classes into the new project, right? Okay, so let's go to, for example, the layer class again. Okay, okay, so let's take a look at the code for the evaluating as an example. Self.s. Okay, so take a look at this line. Okay, this particular line over here. Okay, so np dot in data, for example, this could be x, if it's a very first layer, correct? So we did x times w transpose plus b. Whereas previously it was, I forgot, x times w plus b. There was no transpose involved. Okay, so once again, now this will be, for example, 10 times 784 coming in. This will be, because we transposed it, it will become 784 as 100 as an example. And b is simply 100 size array. So NumPy won't complain, it will do the proper computation, right?
So B will be 10 or by 100, right? B should be changed 10 by 100.
Correct. You mean the delta?
The B, S equal X W transpose
No.
plus B because,
The bias is simply 100.
yeah, but here it will be 10 by 100 because of the S will
No,
be,
the way it does it, this 100 will be added to every column.
but the S is 10 by 100, so the B it should be the same size because
No.
we are going to combine 10 here.
Yeah, so let me explain how the NumPy works. Okay, so S will be, as we discussed, 10 by 100. You agree?
Yeah, okay.
Right? Because this is